on action. That's when you guys are supposed to ask a question or something. So, what we were talking about last time was centrality in general, of course. And initially, we explained centrality with the assumption of undirected graphs. So it's like there's just a tie and it has no particular direction. But most of our data tends to be directed. So we want to be able to compute centrality on directed data. And we showed that for things like degree, it's no problem because we could take the row sums, which gives us out degree, or we could take the column sums, which gives us in degree, and both are useful things. And if you notice, it's not the same nodes that have the same thing. So C, for example, has lots of out degree, 3 of them, but only has 1 in degree. That means that, assuming this is something like likes, C likes 3 people, but only 1 person likes C back. And we have a tendency to prefer in degree because out degree tends to be affected by social desirability things. Everybody wants to say that they're well connected, except for the negative ties, of course. One thing I would point out is that the average out degree, if I took the sum of all these is 12 and I divided by 6, I get 2. And if I did the same thing for the in degrees, I took the average in degree, it would also be 2. And it will be that way in every matrix you ever do. And it was kind of funny because somebody noticed this and thought, well, that's too much of a coincidence that every data set I have, the average in degree is the same as the out degree. So they wrote me and said, your program's wrong. And I said, well, it's a mathematical necessity. And it comes from the fact that every tie has 2 endpoints on it. It has to come out that way. So we see that we can do in degree and out degree, and we can plot them against each other. It's kind of fun. With closeness, we can do out closeness. And here it makes sense too. Out closeness is one's ability to diffuse to the rest of the world. So if you're the one that's sick, how quickly can you get your illness to everybody else? And in closeness is how quickly the world can reach you. So that's how quickly you can hear news that's going on or catch a disease before there's any kind of treatment. And betweenness, we said, no real problem. Betweenness is such that we're just counting how often, say, somebody needs F to reach somebody else, and so we just follow along in the direction of the arrow. So B needs F to get to A. B needs F to get to, they don't need them to get to C because they can go directly to C. Does B need F to get to E? Actually, yes, but, sorry, yeah, you can go around. So you can go from B to F to D to E. So again, F is needed. So, we don't need an in-betweenness and an out-betweenness. It's just plain betweenness. That's very nice. Say it louder. So yes. So there are no incoming arrows to B. So there's no path that ever goes through B. Right, so if you're going from C to B to F, that's impossible because there's no arrow from C to B. So if you only have out degree, you could never have betweenness. And if you never have in degree, you could never have betweenness either. Now, the one that's kind of cool is directed eigenvector. And if you remember, eigenvector is the one where you have a score that's high if you're connected to many people who themselves have a score that's high. It's like you're connected to the well-connected. That's often what we really want, right? And I called it high school kind of popularity. It matters who your friends are. If they're all outcasts, it doesn't really add to your popularity. Well, in math, there is such a thing as a right eigenvector and a left eigenvector. And the right eigenvector corresponds to like an out eigenvector, and the left eigenvector corresponds to an in. The problem is that it is not defined for many, many matrices. It simply cannot be calculated, mathematically impossible. So, and one of those is this one down here. It simply cannot be calculated for that. And either the program will blow up or it'll give you really wacky answers. And yet the concept is good. The concept of an out eigenvector is that you send to people who are themselves big senders, who then send to big senders. And so a high score should mean someone who is a really good transmitter. And similarly, the in eigenvector means that you're receiving ties from the big receivers, which is ideal. That's what you want. That you could only have one tie, but if that one tie is the person that really receives a lot, that's great. So the concept works, the math doesn't. Fortunately, there is a workaround. And the workaround is something that used to be called beta, used to be called Bonesich power, 1987. And then in some papers he called it alpha centrality, and in most papers he called it beta centrality. So I call it beta centrality. And it's defined by this little matrix equation here, which is P is a vector. It's a set of scores. It's like your centrality scores, okay? R1, as you know from last time, is simply the row sums of R. So R1 is actually just the degree of each person. R is the adjacency matrix. It's like who likes whom. Beta is a constant that the user has to choose. And I is the identity matrix. So it's an n by n matrix in which there's zeros everywhere except down the diagonal where there are ones. So we can calculate this in MATLAB or any matrix language. We could do it in UCI Net. And the result of this part of it, oh yeah, and I forgot to mention that this section in the parentheses here is inverted. So the inverse of the identity matrix minus a modification of your data matrix is itself a new matrix. And then we're going to multiply it by its row sums by its degree. I know it sounds kind of arbitrary, but it's not difficult, obviously. You can understand what it's doing. Now, here's what's interesting about it. Under the right conditions, when beta happens to be between these two values, and I'll explain what they are in a second, then this bit that's in the parentheses and inverted is equal to an infinite sum of matrices. Now, let me get back to what these two parameters are first. Lambda is the largest eigenvalue of R. And if you remember when we were doing eigenvectors so far away, where was it? There's the eigenvalue. So the eigenvalue is just a constant. It's kind of a scaling constant. If you remember, I also said that a person's centrality is equal to the sum of the centralities of their friends, adjusted by a constant, a proportionality constant. So that's the sum of the centralities of their friends, then times a constant. That constant's called the eigenvalue. So every matrix has its little eigenvalue, has multiple eigenvalues, in fact, but we take the largest one. Some people do get excited by this. So if beta happens to be smaller than the reciprocal of the largest eigenvalue, or its absolute value is smaller than 1 over lambda, then this thing out here, this inversion, results in this extension, this expansion. Now, what is this? Okay, so this is R to the first. That's just the adjacency matrix. That's just who's friends with whom. R squared is a matrix, it's n by n, that gives the number of paths, actually walks, but the number of paths from any node to any other node that are exactly 2 links long. Exactly 2 links long. R cubed gives the total number of walks from any node to any other node that are exactly 3 links long. And that could be A to B, back to A, and then to B. Okay, so that doesn't have to be a real path, but as long as it's 3 links in there, that counts. R to the 4 is the total number of walks from node I to node J that are exactly 4 links long, all the way out to infinity. Now, if it weren't for the betas, that infinite sum would yield a new matrix which had infinite cells, because you're adding up infinity. But the beta, let's assume for a second that the betas are smaller than 1. So beta 0 here is 1. Anything to the 1 is to the 0 power is 1. So this first one here is just the adjacency matrix. And if it stopped there, by the way, and we threw away everything else, then all this would be is, when we took it to the next step, is the row sums of the adjacency matrix. It would give us degree. But it doesn't stop there. So now let's say B is 0.5. So B to the first is 0.5. So it's going to be 0.5 times the number of walks of length 2 plus 0.5 squared, which is 0.25 times the number of walks of length 3, plus 0.5 times 0.25, 0.0625. Notice that the beta, that the weighting factor is getting smaller and smaller. In fact, when the exponent goes to infinity, that weighting factor goes to 0. So that means paths of infinite length are weighted 0. And so that's why this thing actually converges and yields a matrix here that I call R+, which is the total number of walks of all lengths from I to J, weighted inversely by their length. So here's R+. And it's got 1 to n, 1 to n. We have maybe the ith row here. We've got the jth column here. We look at this number right there. So R plus, and we have ij, is equal to the total number of walks that go from I and end at j of all lengths, all possible lengths, including length 272. But weighted inversely by their length. So the really long ones, like 172 lengths long, hardly count at all. Whereas lengths that are length 1 get counted 100%, because B there is 1, so it gets a full points for direct connection. And if it's a path of length 2, it gets weighted a half. And if it's a path of length 3, it gets weighted a quarter, and so on. So now we've got this cool matrix that gives all the different ways that I can reach J. Short path, long path, and it sums them all up. What a great matrix for understanding influence. Because, of course, influence can take lots of different paths simultaneously. You don't just influence one person, but then influences one other person. Everybody's influencing everybody. So if the original R matrix was who influences whom, then the row sums of this mess here, of R plus, would give us the total number of ways that node I could influence the world. So if you actually got those scores for everybody, you might then pick somebody who has a high score on this measure and say, aha, that's the person that I want to influence, because they can influence the rest of the world. They are the Oprah of my network. Say that again? Is it only looking at distance? Is that what you said? Yeah, and it's not actual distance, because in graph theory we use distance to mean the length of the shortest path, and this is actually all paths that are being considered. And it counts the short paths a lot more than long paths, because it figures, a long path of 270, what's the chance that any signal at all is still left there, right? So it weights those down radically. Is that your question? No, it's network distance. It's the number of links, number of hops in the chain. So, yeah. So it's like you tell someone who then tells someone who then tells someone, but you don't tell just anybody because you only know a certain number of people. You only. It might. Oh, well, that's interesting. Yeah. So. Well, you're in geography, right? And people in geography are well aware that, say, in Appalachia, you might have a community here and a community here, and they could help each other, except there's a major highway right here. And it's difficult to cross the highway. And it's an obstacle for these people to just, even though they're physically close, they can't just hop over and help each other, give each other a cup of sugar or something like that. The way we handle that here is that in our original R matrix, it doesn't have to be ones and zeros. It could be instead that we have person I and person J, and the strength of the connection. Maybe let's scale it from 0 to 1. For this one, could be a perfect 1, meaning there's like no obstacles for them to send there. But for somebody else, it might be a 0.25. Really, it's kind of a low chance that they'll even send anything to K here because of whatever their relationship, obstacles, etc. So that's another nice thing to point out about this measure is that it handles valued data. You can have strength of tie, which can be used to represent all those kinds of obstacles. So we have this new measure, and it has this sense of making use of the whole network, which is great. It's very good, very applicable to influence processes. And it also has an interesting consequence. The beta parameter can be varied. And if you think about it, suppose beta were 0, because you get to choose this. So if beta is 0 here, this is going to be 1, because anything to the 0 power is 1. Don't ask me why. Math is like that. So that's a 1 times r to the first, which is our adjacency matrix. It's our friendship matrix. Plus beta to the first. Well, beta is 0, right? So 0 times this, it just knocks this out. Beta squared is still 0. Beta cubed is still 0. So actually all of this falls away, and that whole thing reduces to this one formula, which is r to the first, r multiplied by 1, which of course is just the row sums of r. It's just degree centrality. So when beta is 0, we have degree centrality. As you increase beta from 0, longer paths are given weight. So if beta is 0.1, then paths of length 2 are weighted by 0.1. Paths of length 1 are weighted full points. But paths of length 2 are weighted 0.1, and then 0.1 times 0.1, and 0.1 times 0.1 times 0.1, and start getting really, really low again. If you make it really large, let's say beta is 0.999, then in the first case, they're getting full power. In the second case, for the paths of length 2, it's 0.9999 times that, so that's still virtually the same as full power. Then we've got 0.999 squared, which is a little bit less than 0.999, but not that much. And it's declining very slowly, which means that long paths are counting a lot. That means that you're studying a process where there isn't a lot of decay as things move. But actually, there are limits to how big beta can be. And that limit is 1 over lambda, which is the eigenvalue of the matrix. So what happens when you make beta as large as humanly possible? Bring it as large, as close to 1 over lambda as possible. When that happens, it turns out that the result here, this row sum, is the eigenvector. So we have a new way of calculating eigenvectors. And that way is by using this formula, specifically that formula there, and simply setting beta equal to 1 over the largest eigenvalue in the matrix. Now, this is interesting because when you have directed data, beta centrality still works. It has an in beta centrality and an out beta centrality, whereas eigenvector falls apart. Can't run it. And under those conditions where eigenvector can be calculated, if you set beta to the right number, you get eigenvector. So there's no reason ever to use eigenvector when you've got beta centrality. It's the larger case that eigenvalue is the special case of, or eigenvector is the special case of. Okay, so let's think about what it would be in the case of an incoming and an outgoing tie, or incoming and outgoing kind of centrality. Can you show me my eraser, Taylor?
I mean, it's not very heavy. I knew that was going to happen.
You were so right about that. Wait, I can. Thank you.
I swear it wasn't my throwing arm. It was just.
It's really hard to throw this thing. Okay, so suppose this is our original matrix, R, and from it we eventually construct this R plus thing, which gives the total number of walks from I to J of all lengths weighted inversely by length.
This is the R plus n squared, right?
Yes, it's always the same. So, this is like Jim, Joe, Mary, and this is still Jim, Joe, and Mary. So it's the same people. And whereas here we just have a 1 or a 0 possibly that says that, yes, Bill has a tie to Joe. Here we're now going to have, there are 15 paths from Bill to Joe weighted inversely by length. Now, what happens, so let's say this is friendship, suppose this is friendship. Or influences, let's do that. Influences. Then the row sum of this is the total number of ways the person A can influence everybody. And the bigger the number, the more they can influence each other, others with shorter paths.
That is the R, that is P, right?
Yes, so this is P right here.
Why is that R plus multiply 1?
So that's to take the row sums of it.
Why is multiply 1?
So like this. So suppose you had a matrix that had 1, 2, and 4, and you multiplied it by 1, 1, 1, and 1, it would sum up the rows. So the row sums then would be kind of how influential each person was. What would the column sums of the same matrix be? Being influence, yeah. It would be influenceability of each person. Influenceability. I cannot spell that. Influenceability. It's how readily accessible they are from the rest of the network. Things can get to them quickly and by multiple paths. That's assuming this is influence. Suppose it is seeks advice from. So now if you look at the row sums over here, that big number there would mean that person A, through many indirect paths, seeks advice from everybody quite a bit. They're like major seekers. Well, what does the column sum mean? Well, that means that A sought Jim's advice via many paths. B sought their advice via the advice. This is a kind of measure of, I would call it, prestige, influence, importance. It's how many people come to Jim for advice, directly or indirectly. Maybe they ask their local expert, who asked their local expert, who eventually asked Jim. And going back to that chart that we had before, where we had a picture that looked sort of like this, maybe it had this. I don't know. I can't remember what it looked like. Let's say it looks something like this. If these people ask advice of these people, then these people are sort of more important and are influential to those people. And then if they're both asking this person is really kind of important because there's this chain of people coming to ask them questions. So finally, you have to kick it up to the boss. At the very top. That's where everything flows to one way or another.
And can you repeat just one more time the row sums?
Yeah. So the rows, well, it depends on what the matrix is here. But in this case of seeks advice, the row sum means that if this is big here, it means that A sought advice from several people who in turn sought advice from several people and so on. So this person just sought advice from like the whole network. Their question is coursing through that network. And it's not particularly interesting, probably, unless you're trying to guess who is going to be the fastest learner. Because that person is putting out the word in such a way that maybe they'll start getting answers coming in from everywhere. Sort of like, putting a message in a bottle and throwing it in the ocean and seeing somebody actually gets it. And, the fact that you throw hundreds of such bottles, some bottles are going to come back with the information. But the column here is more interesting because if there's a big number here, it means that A, through many paths, seeks advice from Jim, and B seeks advice from Jim, and so on. And the sum of all that is that lots and lots of people, through many, many paths, are trying to hear, are going to get the advice of the highest scoring person. Let's see, maybe we should try to think of another example. Let's do has much contact with, physical contact. Especially through hands. And we're interested in cold. So, and this doesn't have to be symmetric, I suppose. Not really true though. I touch your hand, you must touch my hand. No, all right, that's symmetric. So, if we then compute our R plus, so now we know all the different ways that A can get to C here, through short paths and through long paths, and so on. And then we sum it up across all the people that they have contact with. This here will be a number that indicates the degree to which A has the power to influence, to give a toll to the rest of their network. They're so located in the network that they're in a position to really infect a lot of people. What will the column sums be? Risk of infection, and in this case, it's the same thing. And the reason is because touching is one of those things that's bidirectional. So this matrix will be symmetric, This one will be symmetric, and the row sums will be exactly the same as the column sums. So your risk of getting infected is the same as your risk of infecting others. But of course, some kinds of contact may be one direction. So, are we somewhat clear on what beta centrality does? And why it's just so darn good. There is the question with it is, how do you choose beta? The problem with social science theory is that it's never precise enough that you would ever have a theory that you could say, so beta ought to be 0.7. Let me put 0.7 in my equation. Just, we don't have theory at that level. But I'll show you some tricks. So let's play on the computer. So let's start up UCI Net. And, well, I need to switch to the folder that is our class folder, which is Documents UCI Net Data. And, well, we always do this, so let's start with CampNet. I'm just going to display it first, big D, and display CampNet. So it's ones and zeros. Good, we want to start simple. We can add value data later. And we can see that Holly has out degree of 3. So does Brazy, so does Carol. Actually, that's a design flaw in the data that everybody has exactly the same out degree. The reason is that these data actually come from the following data. Do the big D again, but this time do Camp 92. Yeah, sure. So you're at the main menu and you do the big D. And now we want you to put in Camp 92. And this is, I used to teach a summer camp for anthropologists. It was a 3-week camp. We took data after the end of each week, although we forgot to do it at the end of week 1 or lost it. And the CampNet data comes from week 3. You can see that it's valued data. The way we did it, because we were all anthropologists, we do things in a touchy kind of way, which is that we write everybody's name on a card. We put the stack of cards in front of the person, and we say, sort them in order of how much you interacted with them. Put your card first, then put the person you interact with most on top of that, then the person you interact with next on top of that, and so on, all the way up to 17. There were 18 people there, right? So the 18th person, actually including yourself. So these are actually ranks. So a 0 means that's the person that Holly interacts with most, that's herself. She's second most with Pam. Well, first most, let's call it, with Pam. Second most with Don. Third with Pat, and so on. Every row has the exact same numbers from 0 to 17. Then what I did was I dichotomized these data, and I said, well, look, I just want to get the top 3 interactors for each person. And we used interaction because in this small group, we thought that asking who do you like was too scary. Right? So we asked who do you interact with, which we think is a pretty good proxy for who do you like. So to dichotomize this, I'm going to close this window now.
And the advantage of doing that as opposed to a survey, because you could ask the same question in a survey.
Well, we were physically there with them, and so it's nice to be able to do all the things simultaneously. Mm-hmm. You know, with a survey, you get like 80% in the first few days, and the last 20% take another month. So it's that. But the other is the basic belief, especially among anthropologists, that you want people to physically engage with the task. That really wakes up the mind. So to the extent that you can make it into a game or a thing that you do with your hands, the better. So we're going to transform. So I went to transform. And I want to dichotomize. I want to make it into ones and zeros. So I choose dichotomize. And the input data set here is camp 92. And what I want to do is write a rule that says if the value is less than something or more than something, then I want to set a tie. And by default, it's got greater than 0. But that doesn't fit with our data because the bigger the number, the less the person interacts with them, right? In our case, it was like if it's less than or equal to 3, that would get us the top 3 interactors for each person. So and then y equals 1, otherwise y equals 0. And I guess we can live with camp 92 less than or equal to 3. It's kind of a horrible name, but let's just leave it. And notice that it did it for week 2 and also for week 3, because they're both data sets, both matrices in the file. And this week 3 one is the one that elsewhere we call CampNet. So CampNet is just dichotomized version of week 3. Right, so let's close this. Now we know what CampNet really is, and we want to calculate degree centrality. We can go to network, choose centrality and power. And as you can see, it's a favorite area in the field, so there's a lot of options. And let's find, oops, I pressed the wrong button. Let me try it again. Centrality and power. And we're going to pick degree, which is up at the top. So we pick degree. The input network is CampNet. By default, the output is going to be called CampNet DEG, which is acceptable. And it wants to know whether the network is directed or undirected. Ours is directed, but we can just let it figure it out. So auto detect. And the output is going to be raw numbers and also normalized. That seems fine. Why not have the normalized? It also allows edge weights. We could have valued data here or not. Let's just accept it. And we see that our out degree is 3 for everybody. We knew that. But the in degree is of actual use. And then the remaining 2 columns are the same things, but just normalized, just dividing by the number of people that you could have had a tie with, which is n-1 others, by the way. You could have a tie with everybody but yourself. So 4 divided by 17 is 0.18. Then it produces something called centralization. And centralization is a network concept. It's for the whole network. And it's the idea that the network revolves around one person. So the perfectly centralized network would look like this. I'm gonna go to the CLI here. Go to the CLI. That's the command line interface. And I'm going to create a perfectly centralized network. I'm going to say, I'm going to call it X equals make star 18. That means make a star-shaped network with 18 nodes and call it X. And then I'm going to draw X. We'll draw X. And it should look like that. And that's as centralized as possible and still be connected. Everybody's got a tie to somebody, but one person has a tie to everybody, and all the other people only have a tie to that one somebody. That's as centralized as you can get. Draw X means please draw a diagram of a network called X. So let's go back here. And here was our first step was to say, yeah, so I could say draw space make star 18. That would work. Did I? Yeah, how sensitive can you be? Oops, now I said 19. Oh, anyway, that works. So, but the first command is, I said x equals make star 18, and that means go create a data set called x that consists of that star. It's a new network called x. And then I could, while I'm in here, I could do something like display centralization of x. And you see it says 1, 1, 1, 1, 1. It's 100% centralized, according to several different measures of centralization. Now, before I confuse you too much, let's go back to network, centrality, degree. We've got CampNet in there, CampNet deg is fine, everything is fine. We say okay. It produces our centrality measures, which are a score for each person, and then it has the graph centralization. And it has two centralizations because our network had both in and out. In an out kind of a sense, it was not at all centralized because everybody had the exact same number of ties going out. In terms of incoming, though, there was a few people that had more ties than others. You can see, again, that Pam and Steve, this is an endless battle, Pam and Steve each have 5 coming in. Other people have only 0 or 1. So the in-centralization is modest. It's not like a star network. If I close this and go to the CLI and draw CampNet, just draw CampNet, that does not look like a star-shaped network. Right? It's not like everybody's revolving around one node. So it got a centralization score that was weak, 0.12 or something. Does that make sense to everybody? All right, let's do this one more time. I'm going to get out of the CLI. I'm going to go back to network, centrality and power, degree. And now, instead of CampNet, I'm going to put in X. If you remember, X was our highly centralized fake network. So let's run it. It says person 1 has degree 17. They're connected to 17. All the other people are connected to just one person. And so it all revolves around person 1. And so you can see that centralization is 1.0. How does it actually calculate centralization? It takes the centrality of the most central person and subtracts the centrality of each other person. So it's going to do 17 minus 17, 0. 17 minus 1, 16. 17 minus 1, 16. 17 minus, it's going to add up all those differences and then divide by a normalizing constant. And in this case, that division yields a 1.0, a perfect centralization. So a formula that is guaranteed, that is worked out just for degree. I can show you how to derive the formula extremely easily. But you can imagine that there's going to be one node that has 17, right, because that's itself. And then there's going to be 17 times 16. Right, so 17 times 16 plus 0. That's what we're going to be dividing by. Because there's going to be is it 17 times? Yeah, there's going to be 17 times that the difference between the most centralized and the least centralized is 16. It's going to be 16 here, 16 here, 16 here, 17 times that. And so that's going to be the denominator. It gets harder for the other measures, but it's easy for degree. Now, notice that we've got this degree here. Normally, we're going to do something with it. X is a fake network. So one more time, I'm going to calculate the degree of CampNet. But for variety, I'm going to do it in the CLI. So let's go to the CLI and say CampNet. So CampNet centrality equals degree of CampNet. And then I'm going to say, I'm going to display camp set. Now, this is a variable that is in your database. You could look at it anytime. I could display camp set, and it's still there. I could multiply camp set by something. I could correlate it by something. Now, I have a data set called camp ATTR, display camp ATTR. That's attributes of the people who are in the camp network. I don't have much data on them. I know their gender. I know whether they were a participant or an instructor. You can see that the instructors were Gary, Steve, Bert, and Russ. And we also have kind of randomly their betweenness centrality here. I could now correlate degree against those variables. So I could do display the correlation of camp set by ATTR. And it tells me that degree is not very well associated with gender. You might have had a preconception that women have more ties than men. Not true in this data set. You might have had a preconception that the people in charge were more likely to be have more degree. And that is somewhat true. We have to look at the significance of this to find out. But it does seem like the more you are of an instructor, that is a 2 versus a 1, the higher your degree centrality. And then degree centrality and betweenness centrality are highly correlated in this data set, which can be the case. All right? Now, I know I'm beating a dead horse, but I want you to be able to do this. I want to do it now through the menus. Network, centrality and power, degree. I'm going to put in CampNet. And notice that it says that the output data set is going to be CampNet DEG. We have ignored that before, but it's going to be the case. So I press OK. It shows me this output. Now, suppose I wanted to correlate this output, this degree, with something that I know about these people, their income, their grades, or whatever. I could grab this, cut and paste it into Excel or something, but it'd be a pain, right? You don't want to have to do that. So instead, notice that it tells you up at the top that it output the degree data set as CampNet DEG. So a new data set's been created that contains this very output. So I close this, and I could now display CampNet DEG. There it is. And that's the same output as we had before. But the point is, because it's a data set, there's more things we could do with it. We could actually correlate it with something, or we could send it over to Stata. For example, I like to go to the CLI. If I edit CampNet DEG, it puts it into a spreadsheet. I could Control A, copy it, and then Control C, copy it to the clipboard. I could then start Excel. And drop it into Excel. And maybe I have other variables about these people, and then just put it together in one database. And of course, from here, I could also just copy this, and I could start up, let's say, my favorite stat package, which is Stata. And I could go to edit here and paste it in, and now it's in Stata as well. And I guess because we changed the resolution, everything's gigantic in here now. And I could do regress integrity as a function of gender and role. Oh, I don't have gender and role in here. Well, anyway, you understand the point. That you can take the data out of UCI Net and put it somewhere else. Don't make the mistake of trying to cut and paste text files. We could, by the way, do that in UCI Net though. So if I'm in the CLI here, and I've got this CampNet DEG here, I could, what could I do? There's, let's look at CampATTR. It's got these variables here, separate variables. What if I wanted to use those as independent variables to predict degree? I have degree, so I could just say regress CampNet cent, or CampNet deg it was, and then this other thing is CampATTR. And that produced absolutely nothing. Do I have to say regress? I do. I have to regress. I must go back, go back. So the command is up here, regress CampNet on CampATTR. However, it was very unhappy with this data. Why is that? Let me look at CampNet deg. Oh, I know why. Here's what I told it to regress. It picked the first column here, which is a constant. You can't regress a constant. So what I really need to do is pick the second column. I could do that. I could say indeg equals column, just call, of CampNet deg, and it's column 2, or it's column indeg. Whatever. I can either use the name of this column or the number. I'll use the number. And now that's created a data set called indeg. Now regress indeg on CampATTR. And then I get my regression. Yeah. So how far back should I go? Just the left. Okay. This one, regress indeg on CampATTR. And these are the same results you would get in any stat package. There is a little extra though. I'm going to use the up arrow that shows me the last command I wrote. And if I add in here something called yperm that we're going to learn about later, it actually adds a significance test that is calculated using a non-parametric technique. And you can see that here's the classical method that Stata would show you. This is the non-parametric. Of course, they're very, very similar. There's nothing in these data that really require robust standard errors or, any kind of strangeness. So the ordinary test works well. But sometimes you're going to want this kind of more robust regression. You can do it here. How far are we? Oh, yeah. I added a, let's see, there's the command there, yperm, which is a permutation test. And it has a built-in question, why this permutation test? Yperm. All right, now, we've been doing this the slow way. Suppose I want multiple measures of centrality on CampNet. I could go display centrality, open parenthesis, and it gives me lots of measures. It gives me out degree, in degree, out beta centrality, which again, the out is all the same because of this way that we created the data. The in, however, is very interesting. There's an out case step and an in case step. We only had one slide on this. It was last time. But what that means is in how many people can the person reach in k steps? And when we run it automatically like this, k is always 2. So this means that Holly can reach 9 people in 2 links. Also, she can be reached by 9 people in just 2 links. Brazy, in contrast, can reach 4 people in 2 links, and only 3 people can reach her in 3 links. It's the in and the out. Pam and Pat are distinctive in that everybody pretty much can reach them in just 3 links. But they're not as good as spreading. They're better at receiving than they are at spreading. And then look at John. John can reach 9 people, but nobody can reach him. Why is that? Because, well, if I draw count, remember it's the guy John. So what's distinctive about John? There's no incoming ties. So there's nobody in the world that can possibly reach if they're following along the directions, the one-way pass. You cannot reach John. Nor could you reach Bill. No incoming tab. Okay, so we sort of understand here. All right. Let's look at beta centrality. The beta centrality that it chose here is the one that makes it look as much like eigenvector centrality as possible. It chose the largest beta it could. That was smaller than 1 over lambda, as we talked about. But we could choose other beta centralities. I would like to look at a data set called Paget, which we have looked at before. And to remind you, I just typed display Paget, and you see that it's got Pag M as one matrix and Pag B as another matrix. I'm going to separate those 2 matrices. I can do that by typing unpack Paget. And if I unpack Paget, it's going to create 2 matrices, one called Pag M and one called Pag B. So let's just verify that. We'll display Pag M, and it's just a single matrix. I also have a little bit of data on these families. Remember, these are Florentine families during the Renaissance, and the Medici are the famous family here. If I display Pag W, I have a couple of bits of data. One is some kind of index of their wealth, and another one is, I've forgotten what these priors are, but it's like the number of seats they have in some public council or religious groups, or I don't know what, but anyway, it's their kind of public importance. Suppose I want to predict this by using their centrality. And particularly, the one that I'm interested in is beta centrality. So I could compute beta centrality. I'll call it B. B equals beta centrality of Pag M. This is the marriage ties. And then I could display B, and I see some numbers there. And then I could correlate B with the wealth and number of I just can't help it. I have to know what priors are. I go to help, standard data sets, Paget. The number of priorates, whatever, seats on the civic council. Okay. Seats on the civic council. So back to my CLI here. And I want to correlate this with the wealth and priorates. So I could display the correlation of B with Pag W. And wow, I can really predict well. So now in these data, I have no idea about causality, direction of causality. It may be that by being so central and being so wealthy, you become, having so many priorates and being so wealthy, you become central. Or it could be the other way around. I don't know. But at any rate, there's a very strong correlation there. But I don't know if it's as strong as possible because the beta that was chosen was 0.30557799, which the computer just chose to make B be as much like eigenvector centrality as possible. What if there's another beta that would provide even higher correlations? I could say B equals beta cent, and then I think I type complete, I'm not sure. Compare. Let's display B and C. No, that wasn't right. What is it that I have to type? Display beta cent. Compare. No. This is cheating. I'll look at the code and find out. DP mat. Run beta cent. Min beta, max beta, increment, multiple. Why didn't I think of that? Multiple. So now what it does is that it says, all right, I know the maximum beta that's allowable is 0.3 because that's 1 over the largest eigenvalue. And I know the smallest that I can do is 0. So I'm going to calculate all of these different intermediary variables, and we could set the increment to different values. And so each one of these has created a version of beta centrality with a slightly different beta. And we could correlate each of those with wealth. So I'm going to set this B equal to beta cent multiple, and then display the correlation of B with patch W. And if I look at that, well, that's quite interesting. It's not a random pattern. Look at the one with wealth. When beta is as large as possible, the correlation is 0.537, and then it goes, then it goes smaller, it goes higher, goes a little bit higher, goes higher. In general, it's getting bigger and bigger and bigger until we get to beta 0. Tell me what that means. As we make beta smaller, the correlation with wealth increases. Floor is open. That's right. It's not so much the people, but it's the shorter paths seem to have more effect. So when you calculate this measure, counting shorter paths a lot and discounting long paths quite a bit, it turns out it predicts wealth better. And in fact, when beta is 0, it's actually equal to degree. So it turns out that simple degree is the best predictor of wealth in this case. And it's a fairly consistent pattern. There's a slight deviation here where 0.536 is smaller than 0.537, and it goes up to 537. But after that, it's a linear increase all the way up, getting better, 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 which gives you confidence that it's not just some kind of artifact or spurious correlation. It really is that short paths, in this case, are what counts. And this is something that Ron Burt would like very much to hear, because he likes to look at only the ego network around one person and say, all that matters is who you're directly connected to. Who they're connected to and who they're connected to is irrelevant. And it seems like, in this case, he's supported in that. Okay, let's take a break. And I'll show you some other ways of using these measures. If we can get out. Yeah.
So in the node attributes data of the UCI Net, can we enter actual value labels instead of ones and twos?
Unfortunately, no.
So tired.
I'm going to make that change.
Okay.
But
Actually, I needed to do that yesterday, so I created a node label text file and then kind of avoided it something.
Oh.
So I think I did it correctly, but I need to
Okay.
make sure that. But so far, there's no way to do it directly.
There is no way to do it directly in UCI Net. Now, NetDraw will accept, like, if you have gender, it will accept the word male and the word female,
Do you have
Okay.
siblings?
but not UCI Net.
Yeah, so actually what I wanted to do was, do you remember what I asked yesterday
Yeah.
about the density by groups?
Yeah.
And then you show the groups numbers.
Yeah.
So
Ah.
that was very
The girl
confusing.
just
Now there's something you can do. So suppose I go to network cohesion density by groups. If you have the labels for each group as a text file,
Yeah.
so you have like just the word group A, group B, group C, one after another, you can read them in here, and then in the output, it will have those labels.
Yeah, that's exactly what I did
Oh, you
yesterday, but
116.
I just was curious if I can do it more directly.
I'm afraid not.
Yeah. Thanks.
It's good that you found that, though.
Grad school is fun.
What's considered? Oh, sorry. She just said that she was finally making above poverty wages. I was just like wondering what's considered above poverty. Well, I think it might have to do with wages, hours. You would probably make sense. What's poverty? Poverty level is 15,000 in Kentucky for a single person.
three different. I must have missed them because I got a single row.
It was when you created the B.
Yeah.
What did you do? Was that just a display? Yeah. So instead you should have said B equals. Yeah. Okay, so let's have a look at beta centrality and eigenvector centrality on a couple of difficult graphs, and also just try to remember how to input data. So what I want you to do is to take this network over here and put it into UCI Net. And you can just follow along. So I'm going to go to the DL editor, which I find the easiest for typing data in. Make it a little bit smaller here. So I'm going to say that, let's say, A sends to B. And I have a little convention that I use so that I don't have to type too much. I always only, well, these are directed anyway, but if they were undirected, I hate to type in both A sends to B and B sends to A. So I always have it only send to a number that's higher. Like, oh, A sends to B, B sends to C, but I never go C sends to B, go downwards. It saves a lot of typing, and there's a way to make it all work. But here, actually, that doesn't matter because it's directed. A only sends to B, so we put A to B. Then B sends only to C. I put B to C. C sends only to D. D sends to A. And E sends to A. So actually, that's quite simple. This format that we're typing in here could either be seen as a node list. It's A followed by all the people that they're connected to, or an edge list, since every time they're only connected to one other. So it doesn't really matter whether we select node list or edge list, but I think of this as a node list myself. So we'll make that a node list. And I'm going to call this, I see that this is a Roman 3 here, so I'm going to call this a network 3. I press save, and it's network 3. And then it shows it to me. Although actually, if your version of UCI Net is old, it probably doesn't show it to you. But you can always go to the big D here and put in network 3, and then you'll see it. So that should be, now if we look at A should be the receiver of at least 2 ties. Let me see if that's right as I go back to my PowerPoint. A receives 2 ties, yes. Okay. So I think that that's right. Now I'm going to run eigenvector centrality on this. Network centrality, and here's eigenvector centrality. And I will put in network 3 and just run it. And it actually came out with some values. Do they make any sense at all? Actually, they do. That's unfortunate. Because eigenvector can easily crash. There's just many, many kinds of data structures that it cannot do. And it'll just say, I can't do this. But this one it was able to do. How very annoying of it. And A gets the highest score, which is the way I would look at it too. let's compare this result with, I'm just going to, I'm going to make this smaller here. And then I'm going to run Bonasich on this. So that's beta centrality. And we'll put in network 3 and see what it comes up with. Uh-huh. Let's see now. Do the results compare? Actually, they're similar, but they're not identical. Huh. In beta centrality, A and B are much closer together. Let's see what we think visually. A and B. So A receives some short ties, but then A, with all that centrality, is sending that to B. So B is the recipient of highly central person, so that ought to be quite high. So I guess I can kind of see that one. I agree with the beta centrality more, but they both came up with reasonable answers. Let's try the one on the top. Let's try to input that. Let's use the DL editor again. We go to the DL editor, we clear away what's there, and we say that 1 is connected to 3, 2 is connected to 3, 3 is connected to 4, and 4 is connected to 5. Not exactly a tough job to enter these data. And we'll save this as network 1. And I'm going to close that. And then I'm going to run eigenvector centrality on it. Network 1. And boy, it's at least coming up with values. That's kind of amazing. Let's see what these values are. So 3 is the big winner here. And 4 is also a big winner. 5 not so much. Let's see what Bonasich would do in the same case. Not network 3, we want network 1. Much more what I would have expected. So the Bonasich one is really giving the highest points to 5, because 5 is receiving inputs from 4, who is receiving inputs from 3, which is receiving inputs from 2 others. And so to me, that's the right answer. 1 and 2 should get nothing. 3 should get 2 units coming in. 4 should get essentially 3 units coming in. And then 5 should get almost as much as all of those units, except that it's some of those paths are now being weighted low because they're too long. Like the one from 1 to 5 is 3 links long. But loosely, it's getting 1, 2, 3, 4 bits of input. The eigenvector is really hard to figure what it is that it's doing exactly. But it's unfortunately one of these cases where, in fact, it can calculate the result and doesn't say, warning, warning, this is not possible. Okay, so let me show you an application of beta centrality. This is from a consulting job at Towers Perrin. And we had a bunch of information about each person here that referred to the formal organization. So we had their rank in the organization, the number of years they had been in the organization, the number of people who reported to them, and we had some classification of their job title that we converted into a rank order kind of thing, so that, CFO was under CEO and stuff like that. And so we pushed those all together, and we did a factor analysis and created a single index, and then reworked all the numbers so that they go between 0 and 100, just to make it simple. Then we also asked people, who do you go for advice? And that we then ran through the Bonasich measure and took the in degree of the Bonasich measure. And then we just plotted them against each other. So if you get a high score on the informal, that means that people are going to you for advice a lot. And in fact, the people who are going to you for advice are people who themselves people are going to for advice. And if you notice, there's basically a correspondence between high in the formal and high in the informal, as we would expect. I don't know what that correlation is, but that's a big one. It's 0.7 or 0.8 or something like that. But there are discrepancies. And the discrepancies are the ones that are interesting to me. Ollie here is scoring on the informal network way above the expected value. Here's the expected value based on their formal position. So they are actually behaving as if their formal position was way over here, because they're right about the same as SMA here, right? In a sense, they're already operating informally as if they had been promoted, as if they were in their next job. I would say this is somebody that could be promoted into that job right away. And they're also stars. These are people that you want to make sure have a stake in the company. They may be looking for a job at this point, especially if it doesn't look like SMA is going anywhere. You want to do something like that. I think that Behringer here is another example. They're way above the line that represents the predicted value given the formal of their informal. They're just informally much more important. And then you've got people like Hep here who are scoring way below the line. They're high in the formal organization, but people are just not coming to them to discuss matters and to figure out what to do next.
Why? That's normal, right? If you are too high, people will discuss things with you.
Well, look at SMA here, right on the line. They are high in the formal, but also highly important in the informal. People definitely want to discuss things with SMA because SMA really understands the business. Hep maybe has been over promoted, has gone past their point of what is that Peter principle thing that they get promoted beyond their level of competence, or could have a personality issue. Maybe he's just not a very approachable person. This might be a perfect candidate for executive coaching because they just don't treat people very well, so people are kind of ignoring them, which means that that's a wasted talent right there. That's somebody who has something to offer, but nobody's making use of it.
Outliers up high, can that be, would you check to make sure they're not spearheading some kind of a rollout of something or some
Right.
kind of special assignment?
That's true. There could be something just at the time of this data collection that made them very central. I actually have a data set that's like that, where it's a government agency, and at time 2, they roll out a new way of doing things. They used to do things on paper, and now they have to do them on this computer program. And it completely changed who was friends with whom and who went for advice with whom, because certain people that were ignored before but are really good at computers, suddenly everybody went to them, and it changed the social structure. But 5 periods, at the 5th period, the social structure was slowly moving back to the way it was at the beginning. There was that big bump that the nerds had briefly. So yeah, that could easily happen there. Okay, so let's play some more on the computer here. Let's take a data set. I'm going to go to UCI Net here, and let's pick a larger data set for once. I'm going to pick I think well, you know what? I want to give you some practice again in converting data from Excel or some other source into UCI Net, because that's the most important task that you have to do. There is an Excel data set that comes with UCI Net. Hopefully the Mac people can access it and cut and paste it. But if you look in the folder where UCI Net has its data, if you look in this folder here, I'm going to go to my Windows Explorer, my File Explorer, whatever they're calling it these days, and search for stuff that is an XLS file, an Excel file. There is something called Data for Learning UCI Net. So one way or another, if you could please find that data set and open it in Excel. You can't open it in UCI Net. Yeah, that's the right one. It's called Data for Learning UCINet.xlsx. Starts with data. No, I actually, oh yeah, that's what I used.
Yeah.
Oh, no, I didn't. I just copied this and put it into File Explorer, which you don't have. It must be like Finder or something.
Mm.
You need to find that folder,
Right.
but I don't know where it's kept.
Mm. It's
Okay. Does anybody who have a Mac, have they found this folder? Getting there, okay. I have no idea how that works, that UCINet thinks it's in that folder, but it's not the real folder. It's like a simulacrum. Or is there a way in the Mac to search the entire disk? Yeah, okay. And then open,
And which one was it?
it's called Data for Learning. Okay, that's it. Okay, so one doesn't have to know where things are. Just search for them. So it has a number of tabs, if you notice, and if you go, you may have to go to left on this thing to find the one that says DB Code Discussion Network. And I am hoping that there is another DB code. Yeah, oh yeah, and there's DB code node attributes. Great, okay. So everybody find DB code discussion network? These are sacred data. They were given to me by Ron Burt. So if we just grab, actually we don't need the discuss column because it's always ones. So just the from and the to, copy it, and then dump it into UCI Net's DL editor. What's that? And then we go to the DL editor and we paste it in. So this is an edgeless format. You can see that it says that person 4 discusses important matters with 5, person 4 discusses with 7, and person 4 discusses with 8. 7 discusses only with 8. So that's not a node list. This is called an edge list. And it's an edge list 1 because it's all one set of people. And I'll wait for people to catch up. Last time I was waiting for people to catch up, and it turned out not a single person was anywhere near where I was, so it wasn't physically possible. Yeah, okay. Anybody need more time? Okay. or try pasting it into a text file first. Something like that. There are a few Mac to PC issues. All right, so we're in the DL editor. We pasted it. We've told it that the format is an edge list 1. We also have to be careful that it doesn't think that from is a person and to is a person. To do that, we can just say it has column headings, and that means it will ignore the first row in column. Sorry, the first row. And then it may be that it will, Andy, that it might just ignore the blank lines. Try it, yeah, see if it ignores them. I mean, that would be very good programming if it does, and I would feel very good. So I'm going to save this, and this is going to be called dbco.net. And it's dbco because this is a database company. It's actually Oracle. I pressed the little, see that save button up there where I've got the cursor? I pressed that button. Ah, okay, that's because you haven't selected it. So what you need to do is go back to the DL editor here. See where it says data format? You have to choose edge list 1. And then we save this as dbco.net. Save it. And if you have a relatively new version of this, it'll display it for you. It should have around 333 rows. Ah, that's a useful thing to do. What you do is you go to Options, and then you choose choose Helper Applications. And then right here, you type write.exe or WordPad, and it'll find it. Yeah, was it everything wrapping because it was too big? Yeah. Okay. So I'm displaying one more time. I know I do this a lot, but I wanted to check dbco.net and see if it's there. Yes, it is. Looks great. So I'm going to be computing centrality on this. And what's great about these data is that they have performance for each node. So going back to the Excel file, if you go to the right, there's a tab, finally, that says dbco attributes. And I'm just going to grab all of them. And I'm pressing Control-C to copy them. And then I'm going back to UCI Net and go to the DL editor, get rid of what's there, and paste it in. Now, can I help anybody that's lost? And what is it in the Excel file? Let me see. Let me look at my Excel file first. I have 331. We have the same, my network. Yeah, so let me go back to the network. And maybe I copied some extra lines somehow. Oh, you have 331, okay. I think I copied some extra lines at the bottom. Did you do Control-A to highlight everything? Oh,
I just,
you did it by hand like this?
no, I just
Did the
Went across
headings?
the top, yeah, just.
I just,
Well, I'm just afraid. Now I'm concerned about like what it looks like. Okay. So is that where yours ends? Is 10:35? Ah, that would be only one off though, but okay. Let me copy it again. Let me put it into UCI Net. Let me throw away what's there. Let me Control V it. And yeah, it is true that if I were to change the data format to something else, like say matrix, it changes the column headings here. So if I go to edge list 1, now it's no longer checked. Well, no, I don't have it yet. So, and actually I have the ones now too, which I didn't really need. Let me save this as dbconet, see if we get the same answer. And we get 331. Does everybody else have 331 in the network?
Like a bar graph.
Oh, okay. Okay, thank you.
Now I have a chance to close that. Oh, right. Pretty good. 331, I can see.
I don't know what I was supposed to do.
Wrapping.
Oh, I.
You do have 331. Everything's right.
options, help right.
And then see
Now, yeah.
Yeah.
So now, have you
What am I
done
supposed to say to
the
that?
attribute?
DB Conet.
Go over to the attribute.
That doesn't look right at all. Is that?
Yours needs to do this, go to view, and then go to where it says word wrap. And then no word wrap.
Okay, so then why does it look like this? What?
So, is there anybody that's having trouble with the display of large data? Okay, so it just doesn't look,
This is what?
yes.
You can click view.
That's unattractive.
Click the view button, and then just click word
So, view, and then word wrap, and see, I've got no wrap on. Wrapless. Wrap free. And how does, okay, so then you're at the next level. So
I mean, I never went through this. Why are you on that path?
whenever you display something, it comes out in WordPad or Notepad. So when you save this, you might then display it. So I need to catch up with you. I need to grab my attribute data. And Control A, Control C, and then I'm going to go back to UCI Net, throw away what I've got, paste it in, having to remember that this is not an edge list format. This is, I go to the top, this is a matrix. And the first row is column headings, that's right. And the first column is actually IDs, so this is good. I'm ready to go. I press save. And now I've got to call this DBCoATTR, because that's my personal naming convention. Anybody need help? Now, one thing that you may notice is different is that whenever I save in my DL thing, if I'm in the DL header here and I save something, I'll call this test. The next thing that happens is a display of it. That's only because I have a fairly recent version of UCI Net. Older ones don't do that. You have to just do the D yourself. You'd have to go to here, go to the big D, and then put in test, and then you'd get it. All right, we're resting here, making sure that everybody's caught up. What are we naming the attributes? DBCoATTR. Would it be useful if I go through the process again? Yes, it would. Okay. All right, so I'm going to start with the network first. So I'm going to go to the DBCo discussion network in the Excel file and go all the way to the beginning. The discuss column here is all one, so I don't actually need it. So I'm just going to highlight A and B here and copy everything. So now I press Control C to copy to the clipboard. Then I go to UCI Net. I open the DL editor. I get rid of what was there using the plus sign. I paste it. I change the format to edge list. And because there's the from and the to up there, I've got to tell it that those are column headings and those aren't node names. So I get rid of those. Oh, I see now why that would be two separate ones. You were right, yeah. So now I do a save, and I call this DBCoNet. DBCoNet. And it gives me output, and when I scroll all the way down to the bottom, it says 331 rows and columns. That's great. That's what I wanted it to be. You might have to press the big D instead and display DBCoNet and get the same result. So that's the network. Now we're going to grab the attributes. So I have to go to the right here until I find DBCo node attributes. I don't remember if there's anything at the bottom of the file that I should watch out for. No, there isn't. So I'm just going to highlight everything, Control A, and then Control C, put it in the clipboard. I go to UCI Net. I go to the DL editor. I get rid of previous junk. I click away from it and click back in again. Just a little dance. And then I have to remember that the data format is actually matrix. And matrix is the very first one at the top here. First row is column label, first column is row labels. That's great. I then can press save and call it dbco attr, and I am done. All of you in this class are invited to be TAs in our links workshop this summer. Pays between $2,000 and $3,000. When is it?
I'm looking for a job, so I want money.
It's June 2nd. Well, here, let me just check it here. Linksworkshop.org. June 4th through 8th. And of course, you know, if you don't feel comfortable using UCI Net, then you should definitely not be a TA. But if you can do these kinds of exercises without any problem, then I would like to invite you to help out. No, send me an email and, you know.
He will give you a test.
Yes, I'll give you a test. From memory, you'll have to type everything in. It's like, now pretend that the screen says, yeah. All right, so do we all have data, network, and attribute? Excellent. So now I want to link those two together. Actually, you know, I never really looked at the attribute data. So I'm going to go to UCI Net here and just display the attribute data, which is dbco attr, and see what I've got. And the first thing I've got is Z-comp. That's the compensation of each individual converted to a Z-score so that the researcher wouldn't know what kinds of salaries are being paid at Oracle. Right? All we know is who's more than another. And Z evaluation is the evaluation by each person's supervisor about whether they should get promoted next year or not. And some people we don't have that for, maybe because they were these supervisors. So, and then there's a bunch of other stuff: age, whether they're a woman or not, whether they're a manager, an individual contributor, meaning that nobody reports to them, whether they're in the Singapore office, target of some program, I can't remember, B-satellite, I can't remember. So it seems like if any of this network stuff is worth anything, you ought to be able to predict somebody's like performance based on their position in the network. So let's see if we can. Let's calculate some centrality measures. I'm going to close this. And I'm going to go to network, centrality and power, and multiple measures. Probably a mistake, but anyway, multiple measures. The input data set is dbco net. And output measures dbco net sent, that's fine. Directed, undirected, I don't know, I don't care. These are the measures that it's going to compute. That's fine, we can compute all those measures. I think we should just run it. So now we know in degree and out degree for all these people. In degree might be interesting. Who discusses important matters with you? Who's coming to you to discuss things with? So let's use that as our predictor variable. And we could, you know, the easiest and best way to do this would be to move this data into a stat package. But, yeah.
Why wouldn't mine display a 0 whenever I put in dbco net, dbco, and then sent, and it just pops up UCI Net for Windows and a 0?
So let me see. So I'm going to do a display of the very same thing to make sure that we're. And so you did dbco attr or dbco net?
You need DB co ATTR?
Yep.
Okay.
So we've got this. We're going to use, let's predict compensation first, and then we'll predict evaluation. And we're going to use that based on in-degree centrality. Okay? Now, the easiest way to do this is to transfer this stuff to a stat package. The problem with a class like this is that everybody's got a different stat package. So we're going to do the regression in UCI Net, for better or for worse. So I close this. I go to Tools. I go to Testing Hypotheses. This is complicated. Tools, Testing Hypotheses, Node Level, then Regression. Because we can do regression at all kinds of different levels in this program. The node level regression, this is basically an imitation of what you get in Stata. It says, what's the data set that contains the dependent variable? And I remember that it is dbco ATTR. And it says over here, which column? And if you use the little down arrow, it's got the compensation, the evaluation, whether the person's the manager, etc. So I'm going to use compensation. I'm going to predict their compensation using their network structure. I kind of like the idea of their supervisor's evaluation better, but we'll get there. What contains the independent variables? Well, the key independent variable is in dbco net-cent. Unless we change the output ourselves, that's what came out of running Centrality. And if you look at which columns, it says, well, there's out degree, there's in degree, there's all these different measures of centrality that you just computed. I wanted in degree. But it's not enough to just choose it. You have to then press the add button. You press the add button, it now puts it in here as like an independent variable. Now, I also want some control variables. And I can get control variables from dbco ATTR. So I'm going to highlight that and replace here dbco ATTR. And it says, well, which columns? And I'm going to check off a bunch of things like whether the person's an individual contributor, add. Whether they are a manager, add. Whether they are a woman, add. Whether they are in sales, add. Whether they are, I don't know, what level of seniority, add. Whether they're in Singapore, why not? And since I don't know what the other things are, I'm going to skip those. Did I get age? I forgot age, didn't I? So I'll put in age, add. Is everybody able to do this part? Okay. So we have a number of different choices in here. We're going to ignore all of them because it's 12:06 and we just want to get the answer. And we say, okay. Now, it has an R-square of 0.662. That's suspicious because R-squares of 0.6 in social sciences usually suggest you're doing something stupid that's like tautological or something. So I'm a little concerned, but ignoring that for the moment, I now look at all of my individual variables. These are their unstandardized coefficients with some standard errors. The significant tests are the same ones that Stata or SPSS would give you. This is the C stands for the classical significance test. And the P stands for the non-parametric one. And you can see that we could go through all the trouble of using this non-parametric, but really the results are pretty much the same. So what is significant? Well, what's not significant is the variable that I thought would be significant. People discussing stuff with you just does not do anything for your salary, okay? Everything else is significant. Oh, being a woman is not significant. I really question these data. It is negative. Being in a Singapore office, that's good for your compensation. Singapore office, age, all of those make sense. Okay, I'm going to now add some different variables. So I'm going to close this, And I don't want to go through all the menus because that was a pain. I don't know if you can do this on a Mac, but I'm going to press Alt Backspace, and it takes me back to where we were. If you can't do that, then I can show you how to get to the menus again. You go to Tools, you go to Testing, you go to Node, and you go to Regression. Okay. Now, I always felt I didn't want to predict compensation. I want to predict whether or not you're going to be promoted next year, because that's more like your performance that year. And then all the other variables I can leave alone, and I will run it. And by the way, the non-parametric part of the significance here has a random component. So your significance for that column might be different from mine. What can't be different is your significance under the classical test, because that's just a formula. And in degree, again, does not predict anything. In fact, none of these variables predicts anything. So maybe in degree was not the best thing. I'm going to close this. I'm going to do Alt Backspace. And I'm going to change my in degree thing. I'm going to, up here where it says DB coadder, I'm going to put in DB conet dash sets, because that's where all the centrality measures are. Take a look at some other centrality measures. Maybe we haven't talked about this one, but maybe two-step between us. If it works, I'll explain it. If it doesn't work, we'll ignore it. Okay? And I guess I can leave degree. Can I actually delete degree? I can't remember whether you can delete from this thing. Yeah, looks like you can. Okay. Oh, but where? And I haven't pressed add. So yeah, there it is. Okay. So now I've got my two-step between us in there. I run it. R square is 0.05. That's a social science R square. And nothing significant. I cannot predict compensation for this. Now, this data set, though, I can tell you, compensation is predicted by structural holes. Ron Burke gave me the data set. It's guaranteed to work. But centrality here did not do the job. Let's try one more time, okay? I'm just going to throw in a bunch of, we'll put in out degree. We'll put in, I don't know, this local thing and this other local thing and the in beta centrality. I don't know. I'm just taking them at random. You can try your own choices. I just want something to come out. Otherwise, I know you're going to walk out of here going, network analysis, so cool. Doesn't work. Wow. Wow, between this works. Of course, we should be dividing this by about 13 or something. You know, our p-value, do a Bonferroni on this thing, because we basically threw the kitchen sink and something had to come out. But maybe now we could get rid of some of the others and just look at betweenness and see if that is working. So, can I do delete? Then delete. Yes. I don't have to add it. Let me just run it. No, I needed a little bit more than that. Well, anyway, you guys know how to wring significance out of a data set. I won't teach you that. Okay. Let's try. What's that? Oh, yeah, so that's whether or not you're a manager. And so apparently that is predicted, but it's a control variable for us. We didn't have any theoretical interest in it. What we were hoping for was one of the network variables would have an effect. Okay, then. So, all right, if I change the dV to compensation, then my career is saved. I can now publish. Look at all those beautiful scores. What an instinct you have for finding significance. Maybe we should have controlled, when we did compensation, maybe we should have controlled for compensation. Anyway, so many things we could have, should have, and didn't do. The last thing that I want to talk about is the hardest thing. And I'm going to go back to slides. And what I want to introduce is just another way of thinking about centrality. We'll do it quickly. I just want to give you a general idea of how this works. Yes, two things. I don't have time for that one. What I want to show you is something called induced centralities. And it's a family of centralities. And it's a way of constructing a centrality specifically for your data set. See, the trouble with centrality measures is that there's a bunch of them that are out there that have been used by famous people, and you have a tendency in your papers then to use the measure that Woody Powell used in his famous 1980 paper. And it may not be like particularly appropriate for what you're doing. But on the other hand, you can't just sort of invent centrality measures, or it doesn't seem that easy. But I'm going to show you a way of inventing centrality measures on the fly that are appropriate to what you're doing. That's the induced centrality approach. So it starts with a network level statistic that we call a graph invariant. That's something like the average distance between all pairs of nodes, or it's the density of the network, or it's the amount of centralization, or it's the number of friends that people have with each other on average, or any network level statistic we can think of. We calculate the statistic, and then we remove a node, and we recalculate the statistic. And then we define the node centrality as the difference between the two calculations. So the centrality of X is defined as how compact, let's say, the network was when everybody was there, and then how compact it is when you remove that node. It's the contribution of that node to the compactness of the network as a whole. So we could use, for example, degree centrality. Degree centrality happens to be an induced centrality. If we start out as our invariant, the number of ties in the graph, and we remove, so we can calculate them. This one has what, 1, 2, 3, 4, 5, 6, 7 ties, and we remove a node. Oops. Let's say we remove node 6. There's going to be one less tie in the network, and so its contribution to the number of ties in the network is actually its degree. So degree centrality happens to be, trivially, an induced centrality. Flow between this, we want to talk about some other time. One question that arises is whether all centralities can somehow be an induced centrality. And if so, it would provide a whole new definition to describe the family of things that are called centralities. So let's take a look at closeness centrality. Have a look at this network here. We have two nodes, A and B. Now, if I calculate closeness the normal way, so that A is 1, 2, 3 links away from those nodes, it's 2 links away from those nodes, 3 links away from this node, 4 links away from that one. I sum up all of those, it's 14 links away from everybody. B has a closeness of 13. So they are different scores of centrality, right? A is ever so slightly less central. B is slightly more central because a smaller number means more central. Now, if we make the graph centrality be the sum of distances between all pairs of nodes, then we remove a node, we recalculate the sum of distance between all pairs of nodes, and look at the difference. It should be that we should get back the same difference. But have a look at what happens. Here's our original network. Suppose we delete A. Then that part's gone right there. And the network looks like this. Now let's put A back and delete B. That, B was right there, we removed this. Notice that this network over here on the right, the one that has no B, is identical to the one here, which has no A. Since they're identical, no matter what statistic we calculate on both networks are going to be identical. So that means that closeness centrality could not be an induced centrality because closeness centrality gave a different value for A and B. And yet, the induced method would show that no matter what graph invariant you chose, A and B must always have the same value because the residual graph, when you remove them, is identical. So not every measure, then, is an induced centrality. So actually, here's our DB code data. And I created an induced centrality measure using the invariant to be the number of pairs of nodes in the network that are within 3 links of each other. So I'm figuring that the bigger that number is, the more communication there is, the more flow of information there is that's useful. More than 3 links, who cares? But within 3 links is important. So what we're saying here is that some node with a high score serves as a shortcut. They're making other people be only 3 links away. Without that node, they might be 5 links away or 6 links away, but that node is helping bring people together. So I run a regression. This is obviously done in SPSS. And I find that, in fact, my measure here is significant. There's the significance is 0.001. And let's see. Oh, also, because this is BERT data, and BERT has his measure of structural holes, and the measure he likes is called constraint, I threw constraint in as well, just to show that when constraint is in the equation, along with my new centrality measure, my measure is still significant, and his is blown out of the water. Okay? So it's really, maybe what constraint normally was capturing was something that this more directly captures. See, when we get to constraint, when we actually study it, you'll see that it's an impossible formula to understand. But the number of pairs of nodes that are within 3 links of each other is perfectly easy to understand, right? And so it turns out that that does a better job. Now, how much time do I have? Oh, I got plenty of time. Okay. So now I want to show you a very interesting class of invariants that sounds stupid. It sounds like somebody had a little too much time on their hands. It's exactly how this was discovered. But suppose we take any off-the-shelf measure centrality, let's say betweenness, and we calculate betweenness for every node, and then we sum up betweenness across all nodes. And that gives us a single number, which is the sum of betweennesses for the whole network. That becomes our graph invariant. It's a little weird. We computed a measure at the node level, but then we added them all up to get the graph invariant. So here's the case. So we sum the betweenness scores to get the graph level invariant. That's the sum of all betweennesses. Then for each node x, we remove the node, we recalculate all betweenness scores, and we sum them to get the new invariant. And then we subtract from the original one where x was present, and this is the induced centrality, which we're going to call the total centrality here. Then we're going to subtract from that x's actual betweenness as calculated normally without any of this induced centrality stuff. So, for example, here is the Medici. Here is the Paget marriage data. If you were to calculate betweenness, you would find that the Medici get a 48 in ordinary betweenness. Guadagni get a 23 here, right? Albizzi, 19. That's ordinary betweenness. Now, if we do the whole process of summing up all these betweennesses and then deleting the Medici and seeing how much difference there is in the sum, we would get a 73. Now, if we then subtracted 48 from 73, we get 25. What is this 25? 25 is the increase in betweenness in the entire network due to the Medici. The Medici contribute 48 points of betweenness directly themselves, but just by being here, they add 25 points of betweenness to everybody else. How does this work? Well, if the Medici weren't here, Salviati would not have any betweenness, right? Because there'd be no tie here, and nobody needs Salviati to get to somewhere else. Pazzi would not be able to use Salviati to get to Ridolfi here, right? Because there's no line here because the Medici are gone. So the Medici actually contribute to Salviati's betweenness. And Salviati themselves is really interesting, because they give more than they receive. You see, they are the only conduit from Pazzi to everybody else in the network. So they get points for reaching the Medici, they get points for going to Barbadori, they get points to Castellani, they get points for everything. They get 57 points. If you take them out, sorry, they get 13 points. If you take them out, the difference is 57, which means that they are truly contributing a lot to other people's centrality, especially Pazzi's and especially the Medici's, because everybody needs the Medici to reach the Pazzi, thanks to Salviati. But without Salviati, it doesn't happen. And then you get the really cool one, which is Ridolfi. Their actual betweenness is 10. So if we just ordinary calculate betweenness for Ridolfi, it's 10. If you remove Ridolfi and then recalculate the sum of all centralities, all betweennesses, the sum is 9. They actually take away betweenness by being there. By existing, they take away centrality from other people. And that's because they're located in such a way that they become the shortest path. So somebody who might have needed to go around, say from here all the way through Barbadori to get the Medici, no longer have to do that because they can go through Ridolfi. So removing Ridolfi takes away Barbadori's and Castellani's betweenness. So an interesting concept that some people are kind of like, what is it in that movie? It's a cooler. It's somebody who comes over to a hot roulette table, and just by being there, they kind of make the good luck go away, right? So I ran another one of these kinds of things on Bert's data, and I predicted, predicted compensation. Doesn't say which model this is in particular. Oh, compensation right there. And here's my exogenous compensation here, my exogenous betweenness, and it's negatively significant. So it's negatively related to compensation, and it's significant. In other words, making other people more central is bad for your compensation. So don't be too helpful. It could also mean, well, I have in here what rank they are, but it could also mean that people in general who are lower tend to make other people more central by their work, which means that they would also be they would have higher compensation. But actually, I'm controlling for all of that. So somehow, when you act as a link that reduces other people's centrality, you suffer. True, but that's a function of just how these things are the size of the numbers, right? I mean, I can multiply them all by 100, and that would just change all of that. This reminds me of our graduate student, Jesse, who recently graduated. He graduated with only one publication, and he did not get a permanent job. He got a visiting job. Now, he was here for 6 years, and he's one of the most talented people I've ever met. Very smart. Always working on somebody else's project and helping them get their work done. Did not write his own papers and did not get rewarded for it. Just saying. Okay. All right, that's it for today. And I will put up the Camtasia thing tomorrow. Say that again? Yeah, it's become impossible to do just one pub. Because, we don't have the prestige of a big university behind us. It's just Kentucky. And in management, that means, you need two. Probably one fairly good one, and then something else. Yeah.